Good morning, everybody. My name is Gilles Fourestey. I'm the director of the high-performance computing platform at EPFL. So I'm going to talk about the HPC environmental impact. So Manuel said that in AI we like a lot exponentials. I'm going to give you a lot of exponentials. Okay, so first of all, maybe let's go back to the definition of what HPC is. HPC is basically scientific computing on steroids. Okay, so this means minimizing time to solution. Whatever the problem is, you want to minimize the time to get the solution. And what this means in HPC in particular, it means increasing the arithmetic throughput to the maximum. Okay, so the more operations you can do per second, the less you'll have to wait to get your answer. So why am I talking about HPC in general? It's because AI has taken by storm HPC infrastructures. So is this? Yeah, it's working. So what do I mean by that? So this is, if you are not aware of this, so this is a list that is published every year. It's been published for the last maybe 30 or 35 years. I don't remember exactly. So that's the list of the 500 fastest supercomputers in the world. Okay. So this list is the latest one, released in last November, and the fastest supercomputer there is called Frontier. It's in Oak Ridge, in the US, and it's capable of producing what we call 1 exaflop. So that's 1 billion, 10 to the power 18. Double precision, multiplication, so operations, let's say complex operation per second. Okay. This computer has been used to train a model, LLM model. So here I put 170 billion parameters, but actually I read the paper wrong. So they show 170 billion parameters and also 1 trillion parameters. Okay, so this computer was used to train an LLM that is 1 trillion parameters, using, I think, 8% of their GPUs. It's an AMD GPU. We're in Switzerland. We have the CSCS, the Swiss National Supercomputing Center, and they are going to get, so they are assembling right now their latest supercomputer that's going to be one of the most powerful AI-capable supercomputers in the world. Lumi, which is right now the fastest supercomputer in Europe, has reported that 50% of their workload is actually AI, okay? Next to the standard scientific computing, so climate and everything you can think about. Okay, a lot of power is available for AI, that's for sure. The problem is that, well, this power consumes a lot of electricity. So right now, the fastest supercomputers in the world consume around 20 megawatts of power. That's roughly, to give you an estimate, that's roughly the consumption of 20,000 households in Western countries. So that's a lot of power. Okay. Before I go into how we can measure the impact, maybe it's a good idea to understand where is this power consumption coming from. So this is so you know chips and CPUs and are based on silicon, and this is the power transistors, so the silicon transistors, and this is the formula that is giving you the power, the active power consumption of a transistor. So C is the capacitance, and V is the voltage of the gate, and F is the frequency. So for a very, very long time, at every generation, the power consumption has been reduced. Okay, thanks to improvement in silicon technology. So at every generation, which is around 2 years, C is reduced by 30%, V is reduced by 30%, and the frequency is decreased by 40%. Okay, if you add to this Moore's law, so you probably heard about this, the law that is supposed to be dying for the last 15 years. If you have two Moore's law to this, this means that the power density of a transistor is staying constant, okay? And this means that for 1 joule of energy, the performance is increasing. This has been true for a very, very long time. The problem is that this is not the full story. There is another term that is the leakage coming from, that is produced by transistors. Here, in this graph, you have the evolution of the active and the leak power for a CPU. This is coming from a keynote that was given by Gordon Moore in 2003. Okay, very interesting. It's available on the internet. I encourage everybody to watch it. It's very nice. He's talking about exponentials in general, and the title of his presentation is "No exponential is forever." Okay, so this is the active. So that's what I was talking about, the active power consumption of a transistor, and you can see that next to it, the leakage. So the leak power. This is a very, very steep exponential. Up to the point that in around 2005, the leakage was roughly the same as the leakage power was roughly the same as the active power consumption. And this means that the performance per, so the statement that the performance per joule is increasing over time is no longer true. By the way, this is what is called Dennard scaling. Okay, so that was observed by Mr. Dennard in the early 70s, and it held true until 2005. Okay, so he went along with the Moore's law, and this is really the law that died 15 years ago. Okay, very important graph. It's very popular among the HPC community. It's the trend of microprocessors starting from 1970. Okay, so in yellow you have the number of transistor thousands per area, and this is roughly related to Moore's law. So you can see that Moore's law is actually not dying. Okay. In blue you have the single thread performance, and I added here the parallel performance, and I'll come back to this. In green you have the frequency of the CPUs. In red, the power consumption in watts, and in dark, the number of logical cores. So you can see that in around 2005, there's no precise date for that, but something happened. And what happened at this date is that Dennard scaling actually died. Okay. So you could not, so the leakage, so the leak power consumption is roughly equivalent to the active one. This means that, as I said, you cannot rely on increasing the frequency. So before this area, the period was called the frequency scaling area, so the free lunch. If you had the code, so frequency was doubling every roughly 2 years. If you had the code, you just wait for the next generation, and automatically time to solution was divided by 2. That's it. There was nothing more to add to that. Parallelism was hidden from the programmer, so that was what we call ILP, okay, instruction level parallelism, and this ran out completely in 2005. So in order to keep the performance going at the normal power consumption and keep track of the power consumption, vendors had to invent something else. What happened? So what they did is that there were two ways actually to keep the machine going. Increase the number of cores. Okay, so that was the multi-core and the many-core era. So this is BlueGene-Q. That's a very good example of a many-core supercomputer. Okay. And so that was based on, so that's represented here. In order to increase performance at a given power consumption, parallel programming was introduced. When I talk about parallel programming, it's data level programming, what we call vectorization or thread level programming, thread level parallelism. So meaning concurrent programming based on the increase of number of cores that are put together. Okay. The other way is to rely on very very optimized and task-specific silicon. So a GPU is exactly that. Okay, it's a highly optimized silicon for specific tasks. Okay. In particular, if you have something that is synchronous and regular, so very regular workload, GPUs are exceptional. This shows in AI, this shows in crypto mining. That's what has driven the performance increase since 2005. So if I can sum up everything, we left the free lunch era, and now we are in the energy efficiency era, where you need to absolutely control the power consumption in order to get performance. Okay, so this is on the left. This is the average of the peak performance, as I showed you before, of the top 10 supercomputers in the world, starting from 2009. As you can see, performance has increased quite a lot, so more than 500 times over the last 15 years. So this is a very nice exponential. So this new energy efficiency paradigm has kept the performance going over the last 15 years. So the goal is achieved. Okay. In terms of, here is the average power consumption of the top 10 since 2009, and the power consumption only increased by 7 times. So overall, if we put the ratio of those two numbers, energy efficiency of the supercomputers, of the 10 largest computers in the world, has increased by 80x. Okay, so that's a lot of energy efficiency. And it's scaling, once again, it's scaling exponentially. So this is good news, right? This here, I plot the sum of the power consumption of the top 500 supercomputers since 2009. So if energy efficiency is going up a lot, there should be reduced consumption in the end. The problem is that, as you can see, power consumption has increased by has been multiplied by 250 over the last 15 years. So that's a compound aggregated growth of 15% per year. So energy consumption has continued to rise very, very sharply. Here, so we'll talk about this, someone else will talk about this more in detail. This is the expected power consumption of everything that is digital in the world. Okay? So HPC is a fraction of this. So right now we are at 7 gigawatts of power consumption, 7 gigawatts. So that's 7 normal nuclear power plants in order to power those supercomputers. 7 power plants. Okay. Here you have the another very nice exponential. This is going to grow very, very quickly. And here you have the repartition of this power consumption. So better energy efficiency has led to more power consumption. That's kind of a paradox. When we talk about energy efficiency, there is a concept that is absolutely critical. It's called the rebound effect. This rebound effect is actually stating that when something is more efficient, when you have, let's say, so power consumption becomes more and more efficient, the savings that you get for using a certain type of energy is not reflected completely in the usage. So this means, for example, if you have 50% of energy efficiency, you don't reduce the consumption by 50%, but 10, 20, 30, and even so in certain cases, and this is called the Jevons paradox, more energy efficiency means more consumption. That was observed by Jevons, who was an economist in 1865, and he made this observation on the coal usage in England. He realized that getting, so as the watt machine was being improved, usage of coal did not go down, actually it went up. Okay? The reason for that is that when you make something efficient, you reduce its cost and you induce demand. Okay, so this means that more and more people will be able to afford this energy. So there will be more people using so consuming this energy. This means more usage in the end. And it's particularly true in the scientific domain, where if I tell you you can get your solution 10 times faster, you're not going to use less energy, you're going to run 10 times more simulations. You're going to put more physics in your model. Okay, so this is exactly that. So this is the IPCC evolution of the grid in order to compute climate for Europe. It was very coarse at the beginning, and as the supercomputers become more and more powerful, you could increase the resolution of your map. Or you could include more models. So in the 70s, you only had the atmosphere, and as the supercomputers were getting better and better, you could put more physics in it. Okay, so you would use it like a gas. You have the certain amount of energy available, you use it all, even more sometimes. This is also true for AI. So you have a very nice exponential here, as was mentioned before. You can see that the number of parameters that are needed in order to train specific LLM models is rising very, very sharply. Here, this is a paper from OpenAI describing the numbers of flops they need in order to train their models, so 10 to the power 23. That's absolutely ridiculous. So this means that power consumption is going to go up by quite a lot. Okay. How do we avoid the rebound effect? Actually, it's a very, very difficult task. According to economists, there are two ways to do that. Either you tax the increased efficiency so that the cost of computing stays constant, so you don't use more actually, or you educate people to achieve a parsimonious sobriety. This is very related to programming, for example, in order to improve locality of data. Moving data across CPUs actually is using around maybe 100 or 1,000 times more power than to execute a complex operation. Okay, so moving data around is a very, very bad idea in terms of power consumption, or you cap usage. I encourage everyone to read this paper. This is very interesting. This is coming from the University of Chicago, so where the very orthodox economists are coming from, and they have come up with a rough estimate of what is the real price of the ton of carbon emission in the economy. They consider that it will probably be $100,000 per ton of carbon. Right now, it's, I think, 100. So you have to multiply the price of everything by quite a lot in order to get the true price of the carbon emission. I did an exercise. I took the GDP of France, and I computed the carbon emission, both local and imported, and I got so the answer was that all the prices were multiplied by 10 immediately. Okay, anyway, so we need to, in order to cap the usage or do whatever we want here, we need to measure emission. So that's what we are doing at CITAS. So our procedure is an a priori procedure. So what we do is that we get a power consumption of a specific cluster over time, as long as possible, in order to get a baseline. Okay, so this is the power consumption of our education supercomputer. That's for students for master projects and everything. So we measure the power consumption. Okay, so this is in a database in our data center. Okay. Then what we do is that we derive an average power consumption per cluster, or per core, or per GPU. Here, this number that's a very important number. It's a PUE. Is actually the ratio between the power that is coming in and what is available in order to power the supercomputers. So it's not one. It should be one, but there is a loss in a conversion, for example, from AC AC to DC, the water pumps, everything that is needed in order to have the data centers going. This has to be as low as possible. I'm not sure this is 1.6. It should be a bit higher, but okay. So we're already losing power here. We're losing here 6% of the power in order to have the CCT going. Okay. So we have this measure for all our clusters. We have the number of GPUs, CPUs, whatever, the memory, and then we can derive per core or per GPU or per terabyte of data that is stored in our data center. We can derive the power consumption. Okay. Then we can derive the emission of CO2 per core or per GPU or per terabyte using this conversion coefficient from watt to CO2. That's provided by the Swiss energy mix. Okay. Once we have that, we can insert this in our database, and we have a nice tool that is here in order to compute, so keep track of everything that is happening on our clusters, meaning how many jobs are being run for how long, okay, and on what type of hardware. And if we, so you have number of CPU hours or GPU hours, and given this, given this coefficient, we can derive what is the emission of CO2 based on that. Okay, cost is not the cost of emission. Yeah, we have a pay-per-use model, but as an indication to all users, we give we give them their equivalency of emission of CO2. Okay. So this is an a priori way to compute the emission. What is missing from the computation? The CO2 impact of construction and delivery of the machine. So in general, we consider that this is 50% of the total. Okay, so it's more, less, 60%. 60%. Okay, so we need to insert this. Vendors are not particularly forward in this category. They do not really want to communicate about this because this is quite a lot. But there is an initiative which is called PAIA that is gathering information about this. So this is becoming easier and easier to get the information. What is missing also is the central storage. That is not there. Cost of external network, so that doesn't mean the network in the supercomputer, it means the overall network at EPFL, for example, the general network. And so what is, I think, very, very important, and we are currently working on that, we could get the power consumption directly from hardware counters in the CPUs or the GPUs. So this is becoming more and more available in throughout the generations. We need to find a way that to collect those counters that won't affect too much the computations, but this is ongoing. Okay. Yeah, so those are the next steps in order to compute very precisely the CO2 emission. Okay, in conclusion, so we are in the era of energy efficiency. Energy efficiency right now means performance. Okay. But when there is efficiency, there's also the rebound effect that paradoxically negates the efficiency when it comes to overall power consumption. Something that I didn't mention is that economists believe that the higher the rebound effect, the less mature a certain market is. So as the AI market becomes mature, maybe this rebound effect will be less important. There are ways to cancel the rebound effect. So either we impose quotas on greenhouse gas emission, or we tax the efficiency gain. It's probably more fair to limit the environmental impact through quantities than price alone. Based on price, this will probably result in the fact that eventually, in terms of AI, there will be only a few companies that can afford to pay for AI, and all the rest will be in the third world situation. So we have developed a way to track the emission of CO2 on our clusters based on the statistical method, and we are working on a finer grain method in order to get the real value of emission. Thank you very much.